Hello guys, welcome back again. In this particular video, we are going to be learning about chemical equilibrium in chemistry. This is the voice of Peter Dex and you are currently watching Dex Online Science Tutorial. If you are watching this video on YouTube, please do subscribe to our YouTube channel and also like and comment under this post. And if you are watching on TikTok, do well to follow our page and also like and comment under this video. Thank you very much for coming back again. So you are welcome to our fourth video lecture, and the subject is chemistry and the topic is chemical equilibrium. Please take note that this lecture is a complete lecture. It's going to run from the beginning of the topic to the very end. So stay tuned and get your jotting materials prepared as we begin the class. Now we're looking at chemical equilibrium. So chemical equilibrium is an important topic. I mean, very important topic in JAMB chemistry. Not just for JAMB, but for POSITME, WAEC, NECO, GCE, and every other O level exam. Okay. Now, this particular video you are watching will cover all the areas you need to know with lots and lots of examples that will help to ease your understanding. Okay, so let's begin the class, starting with section 1. Now in section 1, we are going to learn the definition and types of equilibrium. Okay, so let's start with the definition in terms of chemistry. All right, so for the sake of chemistry, we are going to be making our definition with respect to chemical reactions. Okay, so now, what is chemical equilibrium? What is chemical equilibrium? Now, chemical equilibrium um, is a phenomenon where a forward reaction and backward reaction takes place at the same rate. Yes, it may not be clear now, but hold on. Let's begin this step by step. Okay. Now, chemical equilibrium occurs in a reversible reaction where the rate of the forward reaction equals the rate of the reverse reaction. Now, what does this mean? When we say reversible, what comes to mind? When we say a reaction is reversible, like what should come to mind? Look at the word reversible, reversible reaction. So what actually comes to mind? It means that the reaction can go forward and at the same time it will go backward. Now, take a look at this equation you can see right here. I mean this particular equation. Okay, so consider that particular equation and you get the exact point I am trying to make in this very class. Okay, now take a look at this. Okay, now take a look at that equation there. You can see A plus B giving us C plus D. Or let me just zoom in. Let me zoom in so that it can be bold and then clear. All right. Now consider this very equation right here and then observe. You can see A plus B is combining to form C and D. And at the same time, C and D is also combining to give us A and B. This equation. Okay. Now, what does this actually mean? Take a look at that very middle. You will observe the kind of sign that is used. I mean, this very sign here. You see that it's not the normal sign for chemical equations. Okay, normally in chemical equation we often use this arrow symbol. All right, this is what we often use in chemical equation. But here you are seeing an arrow like this, and then you are seeing another one like this. Okay, so what actually comes to your mind? Let me make this clearer a little bit, like this, and then you see another one like this. So what comes to your mind? This particular arrow, this one here, that is pointing towards the right, is trying to tell you that the reactant, which is A and B, is actually combining to form C and D. And meanwhile, this other equation beneath, let me just zoom into this one. Okay, let me zoom into this one. Now observe this particular arrow, this one here. This one is actually showing you that this reaction is proceeding towards the right, meaning A and B is combining to form C and D. Okay, now at the same time, observe this other arrow beneath. Okay, now that one is trying to tell you that this reaction is actually proceeding in the opposite direction, meaning reactant C and D, that's this reactant, and the other one other there, is combining to give B, and also reactant A that is on the other side, that's this reactant A you can see right here. Okay, so this is a reversible reaction. When we say a reaction is reversible, it simply means that once the reactant combines to form the product will also combine to form back the reactant, as you can see right here in this equation. That means A and B will combine to form C and D, and at the same time C and D will also combine to form A and B. All right, that is what we mean when we say a reaction is reversible. All right, now get back to the definition. Chemical equilibrium occur in a reversible reaction. That is in the type of reaction where the reactant will form the product and the product will also form the reactant. Okay, but this reversible reaction will only be at equilibrium when the rate of the forward reaction equals the rate of the backward reaction. That means if the speed at which A and B is combining to form C and D is equal to the speed at which C and D is also combined to form A and B, then you can say that the reaction is at equilibrium. Okay, so take note that at this point, the concentration of the reactant, okay, the concentration of the reactants and products remain constant. All right, so the concentration of the reactant and products remains constant. Now, what are the things that must be in place for me to say, oh, this particular reacting system is at equilibrium? What are the things that must be in place? These are the things I have highlighted right here. Okay, that's this one. This ones you can see right here. All right. Now, number one, the rate of the forward reaction must be equal to the rate of the backward reaction. And number two, the concentration of the reactants and products must remain constant. Take note, I did not say they must be the same. I say they must remain constant. Okay, just imagine you are 10 years old, your younger brother is 5 years old. And let's say from ages to ages, your age does not change. You're always 10 years old, you forever remain 10 years old. And your brother, your younger one, is always 5 years. Even in 50 years later, that brother is still 5 years old. That's your age are not the same. Your own is 10, that of your brother is 5. But meanwhile, both of your ages are constant, meaning your age does not change. The age of your younger brother does not change. Okay, that's what it means when we say the concentration of the reactants and product must be constant. They must not be equal. Just the way that of your age and that of your brother is not equal. Okay, but they must remain constant, meaning they must not change. You get? So for a reaction to be equilibrium, the concentration of A, B, C, and D, that's all the reactants and all the products, all of them must remain constant. And also take note that at equilibrium, the molecules continue to react. If they stop reacting, then the system is no longer at equilibrium. Okay, now you need to know that the type of equilibrium that is seen in chemical reactions is actually a type of equilibrium called dynamic equilibrium. All right, dynamic equilibrium, you can see right here. Okay, dynamic equilibrium. When we see dynamic equilibrium, what does it mean? You can see it's highlighted in yellow. Dynamic equilibrium means that the forward and backward reaction continue at equal rates, while the concentration, that the concentration of all the reactant and the products, remains constant, not equal. I'm saying this for the second time. Now let's take example. Example one is the reaction of bromine with water to form bromine water. All right, now you can see the equation right here. Up there, you can see it's highlighted in bold text. Okay, now this is it. Now you can see bromine reacting with H2O to form bromine water and hydrogen bromide. Okay, you can see the equation in the midst of them. The symbol in between. You can see the symbol is the symbol for a reversible reaction. Okay, it's the symbol for a reversible reaction. This particular symbol. All right, that's to tell you that the reaction is actually reversible. All right, so at equilibrium, the bromine molecules are reacting with the water to form bromine water and hydrogen bromide. And at the same time, hydrogen bromide will still react with bromine water to form both water and bromine. Okay, so this right here is bromine water. This is hydrogen bromide. This is the bromine itself, and this is water. Okay, please take note of that. So the reactants are forming the product, and the product are forming the reactants. Now you can see another example, the Haber process. The Haber process is a well-known example of reversible reaction. And for this reaction to be at equilibrium, you can see nitrogen, you can see hydrogen, and then you can see ammonia. Okay, so the nitrogen must react with hydrogen to form ammonia, and at the same time, ammonia reacts with the compost to form the hydrogen and the nitrogen. And once it happens at equal rates, then the reaction is said to be at equilibrium. Now you can see another third example right there, which is nitrogen dioxide equilibrium, where you can see NO2 forming N2O4 and N2O4 also forming back NO2. All right. Now, in chemistry, we have two types of chemical equilibrium. All right. There are two types of chemical equilibrium. The first one is homogeneous equilibrium. Okay, homogeneous equilibrium. When we say equilibrium is homogeneous, what does it mean? Take a look at this here. It simply means that all the reactants and products, they are all in the same phase. When we say the same phase, what does it mean? It means the same state of matter. If they are all solid, then they are all solid. If they are all liquid, then they are all liquid. If they are all gas, then they are all gas. And if they are all aqueous, then they are all aqueous. Now, take a look at example 4. Okay, take a look at example 4 right here. Now, this is example 4. Okay, now you can see SO2 and take a look at the state. You can see that it's a gas. Okay, let me zoom in. All right, now you can see those stuff in bracket. Okay, like this. This is gas, this is gas, and also this is gas. Okay, you can see that there is a small letter G in those brackets. Those letters there is telling you the state of matter. Okay, so they are all gases, and they are at equilibrium, meaning this is homogeneous equilibrium. Now, also take a look at example 5. A good look at example 5, you can tell that all the reactants and products are all in the same phase, meaning they are all aqueous. Okay, whenever you see that what's in that bracket is letter G, then it means gas. If it is AQ, it means aqueous, and if it is S, it means solid. If it is L, it means liquid. Okay, now the fact that this guy is aqueous, this is aqueous, this is aqueous, means that they are all in the same phase. This is aqueous, aqueous, and aqueous. So they are all in the same phase, meaning this is homogeneous equilibrium. Now, for heterogeneous equilibrium, the reactants and products are in different phase, okay? They are all in different phase. Now, take a good example at this particular equation right here. You can see that calcium carbonate is solid. Calcium oxide, which is one of the products, is also solid. And meanwhile, CO2, which is carbon dioxide, is a gas. So it means that all of them are not in the same state of matter. They are not in the same phase. So it means this is heterogeneous equilibrium. The same thing is observed in example 8. You can see silver chloride is solid. You can see the silver ion itself is aqueous. Chloride ion is aqueous. So the fact that all of them are not in the same phase, it means that it is heterogeneous equilibrium. Okay? The same thing is observed right here in example 9 and example 10. Now, that's for section 1. Now, in section 2, we are going to be looking at the conditions for chemical equilibrium. That means for a reaction to be at equilibrium, for a reversible reaction to be at equilibrium, what are the things that must be in place? There are things that must be in place for me to say, oh, this particular reversible reaction is at equilibrium. What are those things that must be in place? Number 1, the system must be closed. Or in other words, the reaction must take place in a closed system. All right? It must take place in a closed system. If it is in a closed system, no reactant or product can escape. But if it is an open system, there are some reactants or some products that will escape. And once they escape, the reaction will stop. Okay? For reaction to continue, all the reactants and products must be trapped in a closed system. If it is in an open system, then the reactants and products will be free to escape from the reaction. And once they escape from the reaction will no longer continue. Okay, so the first condition you must always remember is that it must happen in a closed system. Okay, now take a look at this example right here, example 11, to illustrate how important the closed system can be. Okay, take a look at example 11. Now, you can see the reaction right there. That's the reaction between, that's the decomposition of calcium carbonate. I'm talking about this particular reaction right here. Okay, that's the decomposition of calcium carbonate. Now, it decomposes to form calcium oxide and carbon dioxide. So, if this is an open system or an open container, CO2 is a gas and it will evolve and escape, and equilibrium cannot be formed. But in a closed container, CO2, which is a gas, will not be able to escape, so it will remain, and then equilibrium will be established. Equilibrium cannot be established when one of the product or one of the reactants is escaping. All of them must be present for equilibrium to be accomplished. Okay, so that's the first condition. Second condition is that temperature must be constant. Temperature must be constant. Very, very important. Okay, because a change in temperature can shift the equilibrium and, destabilize the equilibrium, and then the system will have to adjust itself again to return back to equilibrium. Please take note, not just temperature. Concentration too must be constant. And if it's a reaction that involves gas, take for instance the reaction in example 11 that you can see right there, you can see CO2 is a gas. If there is gas in that reacting system, whether it's a reactant or a product, I don't care. If there is a gas, then pressure too must be kept constant. If pressure is not constant, then equilibrium will never be accomplished. Now, number 2 is that the reaction must be reversible. Okay, it is only in a reversible reaction that is where equilibrium can be accomplished. Okay, you can take a look at example 12, and you can see a reversible reaction and an irreversible reaction. Okay, so in a reversible reaction, the reactants will form products, and product will form reactants. Reactant will form product. Like they will just be exchanging. They will just be there exchanging each other. Reactant will change to product, and product will change to reactants. But if it is irreversible, all the reactant will change to product, and the product will not change back to reactant. So the reaction will stop. Do you get? So that is the third condition, and these 3 conditions are very important if equilibrium must be attained. Now we go over to section 3 of this class, which is equilibrium constant. We are going to be learning about the equilibrium constant in this particular class. All right. Now, first of all, what is equilibrium constant? The equilibrium constant expresses the ratio of product to reactant. Now, when I say it's a ratio, what do I mean? When I say it's a ratio, it expresses the ratio of product to reactant. What do I mean? I mean that in the equilibrium constant is a fraction. Okay, it's expressed in a form of fraction. All right. Now, in this fraction, The product is usually the one occupying the numerator, and the reactant occupy the denominator. Okay, now observe this particular reaction you can see right here. Okay, this particular example. Now observe this reaction right here. Okay, now take a look at it. You can see that reactant A is combining reactant C to form D. I'm sorry, reactant A is combining reactant B to form reactant C, to form product C and product D. Okay, so A and B are the reactants, C and D are the products. Now observe the fraction right here. Take a look at the numerator. You can see that it is C and D. And take a look at the denominator. You can see that it is A and B. Okay, so the reactant is always at the denominator and the products are the numerator. Now, the powers of the products and the reactants are their coefficients. Now, let me zoom in for better understanding. Okay, now let's zoom into this particular equation. Okay, let me zoom in to fit in. Perfect. Now, take a look at this. This is reactant A. Okay, this is reactant A. This is reactant B. This is product C and this is product D. Okay, now observe. You can see that for reactant A, there is a small letter A behind it. Reactant B has small letter B behind it. Reactant C has small letter C behind it. And then, sorry, product C and product D, they have small letter C and small letter D behind them. So those small letters represent their coefficients. When I say coefficient, what do I mean? I mean those numbers that represent the number of moles that are used. Okay, now let me give you an example of a real life equation so you understand what those small letters mean. Okay, let's flip to the next page. Now take a look at this reaction right here. Take a look at this reaction, this particular one. I mean this one right here. Now observe this reaction. You can observe that there are two reactants here and one product. Okay, now take a look at this product. You can observe that the product is SO3. Meanwhile, there is a 2 behind it, this 2 here that I just covered. Okay, now that 2 there is the coefficient. Observe this reactant SO2. You will notice that there is also a coefficient behind it that I just covered now. Okay, that's the coefficient. Now observe this reactant oxygen. Okay, observe this oxygen reactant too. You see that there is no number behind it. Okay, you can observe that there's supposed to be a coefficient here. Sorry, right here. Okay, but there's nothing right there. That's to tell you that the coefficient is 1. Okay, when you see that there is nothing standing before an atom in a chemical reaction, just know that there's an invisible 1 right there. All right, so you can see that the coefficient of SO2 is 2. Okay, of SO2 is 2. That of oxygen is 1, is not written, and that of SO3 is also 2. That's this number right here. Okay, now in chemical equilibrium, let me go back to the previous page. Now returning to this one, I believe you now understand what these small letters stand for. They stand for the coefficient. They are always behind the reactants and the products. Okay, now whenever you are expressing your equilibrium constant, make sure that the reactants are the denominators, that's these guys here, then the products are the numerators, and both reactants are product, they are raised to the power of their coefficient. Very important, make sure that they are raised to the power of their coefficient. And also you must ensure that you put them in this box bracket. You can see this box bracket, very, very important. Okay, without those box brackets, your equation is actually not correct. Okay, now in this particular equation, Kc actually stands for the equilibrium constant. Okay, Kc stands for the equilibrium constant. The square bracket means concentration. Okay, so you can see C in bracket in that particular equation. That C in bracket means concentration of C. D in bracket means concentration of D. A in bracket means concentration of A. And B in bracket means concentration of B. That's what that bracket is. That's why you must add that bracket. Because if you don't add the bracket, you will not know that you are trying to say concentration. Because that's what the bracket means. It means concentration. So I believe if you are used to chemistry, you must have seen something like this before. Maybe H, you see plus on top. And then you see something like this. This actually means concentration of hydrogen ion or hydrogen ion concentration. Okay, that's what this box bracket actually means. This particular box bracket you can see right here. All right, now let's return to what we were saying. Now the square bracket means concentration, and this A, B, C, and D I've explained before, they mean the coefficients from a balanced equation. Okay, now what are the rules you must follow if you are going to write the equilibrium constant of a reversible of a reaction at equilibrium? What are the rules you must follow? You see, these rules are very important, and it's very crucial that you take note of all of them. Okay, you need to take note of them. Very, very, very important, because JAMB, post-UTME, and all of that level O-level exam, they often test students on their ability to write out the equilibrium constants for reactions like this. Okay, now what are the rules? Number one, the product goes to the numerator. I have explained this before. The reactants goes to the denominator. I have explained this before. Number three, each concentration is raised to the power of its coefficient. I have said this before. Okay, and number four, only gases and aqueous solution are included. Okay, that means in this particular equation right here, you are not permitted to introduce a solid or a liquid into this equation. The only thing that must enter this equation right here are gases or aqueous solution. So take for instance, if I see this reaction and I see that, let's say A is a gas, B is a gas, let's say C is a gas, and then D is a solid, I will eliminate D and only work with A, B, and C. Okay, so when writing your equation, you must not include is a solid or a liquid, only gases and aqueous. You get that in the examples. Okay, and secondly, that number five, pure solids and pure liquid are not included. And then finally, the Kc value is constant at any given temperature. You should always bear that in your mind. All right, now let's look at some examples in all those stuff we just finished explaining. Now this is example 13. Okay, now we are looking at example 13. This is example 13 right here. Now observe this particular equation. Observe the equation. You can see that they are all gases. Okay, please take note, before you write the equilibrium constant of any reversible reaction, you must first check their states. Make sure they are either gases or aqueous. If you see any solid, assume you didn't see it. If you see any liquid, assume you didn't see it. Just work with the gases and the aqueous. Okay, now remember that the product goes to the numerator and the reactant goes to the denominator. Okay, so because of that, I'll write my Kc equal to, on the numerator you can see SO3. All right, let me zoom in. You can see SO3 right there, and SO3, after writing, I put in a bracket and raise it to the power of 2 because the coefficient is 2. You can see it right here. Okay, the coefficient is actually 2, so that's why I have to raise it to the power of 2 on this other side. All right, now take a look at the reactant. I'm done with the product. The reactant goes to the denominator, right? Yes. Now observe, this is the first reactant. Okay, that's SO2, so I'm going to put SO2 in a bracket and raise it to the power of its coefficient, that's 2. Now the second reactant here is oxygen, so I put oxygen in bracket, and then of course you know there is an invisible one right here. Okay, there's an invisible one behind it, so I can choose to raise it to that power of 1 and put the 1 on top, or I can choose to leave it like that, but it's always much better to leave it like that. Okay, you don't raise to the power of 1 because raising to the power of 1 means the same thing, so you don't just bother raising it to the power of 1. So this is how to write the equilibrium constant for a chemical reaction. All right, now you can also see example 14. Okay, now example 14, we are made to write the equilibrium constant for this particular reaction that has to do with the decomposition of calcium carbonate. Okay, you can see CaCO3 is forming CaO plus CO2, and at the same time CaO and CO2, they are combined to form CaCO3. So it's a reversible reaction. So what are we going to do? Let's write the equilibrium constant for this particular this particular reaction at equilibrium. So what are we going to do? First of all, observe the states of matter. Now you can see that calcium carbonate is solid, the calcium oxide, which is CaO, is also solid, and only CO2 is the gas here. So we are not going to work with these two guys, we're only going to work with this particular one right here. Okay, so if I'm going to write my equilibrium constant, in the numerator I'm going to put this, and in the denominator I'm not going to put anything. Okay, that's why my Kc is equal to just CO2. There is nothing on the denominator. Alright, so I can choose to write it as something like this, you know, write my CO2 and then put it on a bracket like this, and then put it divided by 1 because there's nothing in the denominator. But anything divided by 1 will still give you that thing, so I choose to remove the divide by 1, leave it as just CO2. Okay, and that is what you can see right here. Alright, now if you observe, what I actually did was that first of all I did it the normal way. Okay, and after doing it the normal way, I now see that this guy is solid, this guy is solid, so I will cancel them out of my equation. Cancel this one, I'll cancel this one, I'm leaving just CO2 behind. Okay, so that becomes the final equilibrium constant. All right, now you can see I wrote notes. CaCO3 and CaO are solid, so they are excluded from the constant. Now take a look at example 15. You can see the reaction given, and if you observe, you will see that all of them are gases, meaning they are all permitted to go into the equilibrium constant. Okay, so these are the products right here, NO and H2O. So that's what I just did. I put them in their place, raise them to the power of their coefficients in the numerator. Okay, and also ammonia and oxygen are in the denominator, and I also raise them to the power of their coefficient. Yes, writing equilibrium constant is that easy. All right, you can also observe similar pattern is followed in example 16. Okay, now the same thing happens in example 17. I eliminated all the solids. Okay, observe the equation very well. You will see that um this guy is solid and this one is solid, but this one is a gas and this is a gas. Okay, so I only focus on those gases and eliminate the solid. So the only gas product I have here is this. So that's why you can see it in the numerator, and the raised to the power of its coefficient, that's 4. And then you can see this one again is a gas, so that's the only thing you can see right there on the denominator, raised to the power of its coefficient. Now example 16, example 18, example 19 all follow the same process. Okay, now over to the next page. We're going to look at the equilibrium constant for just gases. Now for gaseous reaction, we can use partial pressure instead of using concentration. Okay, we can use partial pressure to express their equilibrium constant. Okay, so it's still going to be a fraction. You're still going to have your product at the numerator and reactant at the denominator, but this time you are expressing them in terms of partial pressure. Now observe this equation for me. See that they are all gases. Okay, they are all gases, and observe this guy here. You can see that my Kc have changed to Kp because I'm no longer expressing the K in terms of C, which is concentration, but I'm not expressing K in terms of P, which is partial pressure. Okay, now observe that I am no longer writing. Let me zoom in. You can see that this is no longer C raised to the power of C, D raised to the power of D, A raised to the power of A, and B raised to the power of B. But you can now see I'm adding extra P behind them, and the type of bracket I'm using have changed because that bracket that looks like a box, that one is used to express concentration. So I'm no longer working with concentration, so I have to change my bracket. All right. Now observe that I added a P to all of them. Okay, there's a P to all of them now. That P there means partial pressure. So this is no longer concentration of C. This is now partial pressure of C, partial pressure of D, partial pressure of A, partial pressure of B. It's still the same method. Just make sure you move the square bracket and replace with this normal bracket that you used to know, and also add P to all of them, both the reactants and the products. So you can see an example right here. Okay, so observe this example. Observe this example very well. You can see that they are all gases. So I'm going to express my constant in terms of pressure, partial pressure. So what am I going to do? This is the reactant, NH3. I'm going to put it on the numerator, as you can see right here. And then I also raise it to the power of 2, which is its coefficient. You can see the power of 2 right here. But just that this time, instead of writing NH3 in the bracket, I'm putting PNH3. That P means partial pressure. So partial pressure of NH3. And then also observe the denominators. These are the reactant here. So I'm actually putting them in the denominator. And you can see, of course, I followed the normal method, raise them to the power of their coefficient, just that I introduced a P inside the bracket. That's just the difference, okay? That P is trying to tell you that this is no longer concentration we are working with. We are now working with partial pressure, okay? You can also see the same thing in example 22 up there. Okay, now let's go back to section 4, which is Le Catelier's principle. And this is the aspect of this topic that mainly draws attention, okay? Now, this principle was stated by Le Catelier, and the principle actually says when a system at equilibrium is disturbed, it shifts to counteract the disturbance. What does that actually mean? It means that once the system is already at equilibrium and then something comes in to alter that equilibrium, the equilibrium constant will have to adjust itself in order to restore itself back again to equilibrium. All right, now what are the different factors that can alter the equilibrium? Number one, you have change in concentration. Okay, the effect of concentration changes. Now, a change in concentration, how can this even alter a system, a chemical system that is at equilibrium? Okay, now take notes. Whenever you add a substance, when you add a substance to a system that's already at equilibrium, okay, that's you increasing the concentration of that substance. Take for instance, let's say nitrogen and hydrogen are reacting to form ammonia, and then the ammonia is also decomposing to form nitrogen and oxygen. And then I come in and then I added more ammonia into the system. So that is the concentration of ammonia has increased because I added more. Okay, so adding more ammonia into that system will actually, increase the concentration of ammonia. All right, and remember that for a system to be at equilibrium, the concentration of all the reactants I put on must be constant. So if I add more ammonia, the concentration of ammonia will increase. So that will disturb the equilibrium. Okay, so adding more of a particular substance into the reaction or removing from it will always alter the equilibrium. Okay, so how will this equilibrium adjust itself? Remember that the Cartesian principle actually says that if it is disturbed, the equilibrium constant will shift. Okay, it will shift to adjust to return the system back to equilibrium. Okay, so now how will concentration change the concentration actually alter the equilibrium? And once the equilibrium has been altered, how will it shift to return itself back to equilibrium? Okay, that's what we want to know now. All right, so in order to completely understand that, you need to know that adding a substance shift equilibrium away from it, and removing a substance shift equilibrium towards it. All right, so take for instance, I remove substance from the reactant side. It means that the equilibrium constant will shift towards that reactant. And if I remove from the product side, equilibrium will shift towards that product. If I add more reactants, equilibrium will shift away from that reactant. That means shifting towards the product. And if I add to the product, equilibrium will shift away from that product and shift towards the reactant. Okay, now take a look at example 25 right here. Now you can see example 25, observe the equation. You can see nitrogen reacting with hydrogen to form ammonia. That's the Haber process. Okay, so adding more nitrogen will shift equilibrium to the right. Okay, so it will move equilibrium towards this direction. It will shift equilibrium to this direction. That means shifting it towards the right. You know, this direction is the right and this direction is the left. All right, so it will shift equilibrium towards the right. Why? Because you removed from the product. This is the product. Okay, that's the product, the ammonia. So if you add more hydrogen, which is a reactant, or sorry, more nitrogen or more hydrogen, it will cause the equilibrium to shift towards the product side, because the equilibrium will always shift away from where you are adding and shift to the opposite direction. But if you now add more of ammonia, what if you now add more of ammonia and you did not add more of nitrogen and hydrogen? If you add more of ammonia, the equilibrium constant will shift away from ammonia and shift towards the left. That means towards those reactants, which is nitrogen and hydrogen. So that's how equilibrium constant shifts with respect to concentration. Okay, now observe example 26 up there. Observe example 26 right here. Okay, this is example 26. Now this is the same reaction we are working with again. Now observe the reaction and observe the notes I added. Observe it very well. Removing NH3, which is ammonia, shift equilibrium to the right. Okay, so this is ammonia. Remember that if you remove from anywhere, equilibrium will shift towards that direction. Okay, now use this illustration to catch it. Imagine you are in your father's house. Okay, let's say you are a kid. You are let's say 7 years old, and you have a younger brother. Your younger brother is let's say 5 years old, or let me just say you are age mate. Okay, you have a twin. All right, you are the senior one, or maybe you are the junior one. Yeah, you have a twin, boy. Let me just say boy for instance. Now the two of you are in the house, and then your father brought oranges. He brought oranges, and then you and your brother went there to drag for the oranges. Let's say there are 10 oranges. Your father dropped it in the parlor, and you all ran there, the two of you. You were dragging for the oranges, and you were able to secure 7 of that orange. And your brother was able to secure 3 of that orange. Just 3, and you secured 7. And now your father came into the parlor again with some extra orange. Let's say 2 extra orange. And then you have 7. Your brother has 3. And then you are going to meet your father again to collect the orange from your father. Your father will look at you and say, Omo, you have 7 already. Your brother has only 3. So your father will move away from you that has a lot and move towards your brother that has only little and give more to your brother, so that at least you guys can have equal, or even if it's not equal, almost equal. You get? So in the same way, if let's say your brother has a lot and your own is very few, your father will come to you and give you more, so that your own can be equal with that of your brother, or maybe almost equal. Okay, so that's why equilibrium is shifting. So just assume now that let's say you are the reactant, your brother is the product, and then your dad is the equilibrium that is shifting. Now observe that your dad will always shift towards the person that has lower concentration. Okay, as in the case now, move towards your brother that has only 3 orange, while your dad moved away from you that had 7 oranges. So that's how equilibrium also shifts. So now imagine that this system right here, you can see right here on the screen, this particular system is at equilibrium. Okay, and then
you now came in and removed some of the ammonia, what do you think? The concentration of ammonia will decrease. It will become lower than usual. So because of that, it will attract the equilibrium. So equilibrium will now shift towards ammonia, and ammonia is a product. So equilibrium will now shift towards the right. Okay, equilibrium will now shift towards the right. And if you add more nitrogen and hydrogen to this reactant system, it means you have elevated the concentration of nitrogen and hydrogen. So equilibrium will still shift towards the right, towards the side of ammonia, okay, to increase the production of ammonia, so that ammonia will also increase with them. Do you get? In the same way, if in this system you remove hydrogen, or you remove nitrogen, or you remove from the two of them, if you mistakenly, okay, let's say you did on purpose, you remove from nitrogen, or you remove from hydrogen, or you remove from the two of them, remember that they are reactants, they are on the left side. So because you remove from them, their concentration will decrease. And equilibrium constant love those that have lesser concentration. So the equilibrium constant will now move. Like, how dare you remove from them? The equilibrium constant will move towards their side. Okay, that means it will move towards the left. It will shift to the left. Okay, and also if you add more to ammonia, what will happen? Because the concentration of ammonia has increased above that of nitrogen and hydrogen, the equilibrium will still shift towards nitrogen and hydrogen, as towards the left. Okay, so anywhere you add to, the concentration there will increase. It will make the equilibrium to shift away from that direction to the opposite side. And if you remove from any part, because you remove from there, the concentration at that place will reduce, so equilibrium will shift towards that direction. So generally, equilibrium shift towards the part that have lesser concentration. Okay, when we now say equilibrium shift towards, let's say in this particular reaction, we are saying equilibrium is shifting towards the right. So what does it mean? It means that more ammonia is being produced. While if equilibrium is shifting towards the left, it means more of the reactant, that's nitrogen and hydrogen, is being produced. Okay, that's why I actually wrote right here that removing NH3 shifts equilibrium to the right, so that more ammonia can be produced continuously. All right, now you can also observe the same thing right here in this particular spot in example 27. You can observe the same thing right here. Okay, observe this example 27. You can see that in this particular reaction right here, you can see that SO2 and oxygen, they are the reactants, and SO3 is the product. So adding SO3 will shift the reactant to the left. I'm sorry, the equilibrium constant, or the equilibrium rather, to the left. Okay, why is it shifting to the left? Because bro, you just added more of this guy. So because you added more of that guy, equilibrium will say, no way. Since you add more of SO3, I will shift to the other side, so that those guys will also gain some more. So equilibrium will move this way. Okay, so if you add more oxygen, oxygen is a reactant, so equilibrium will move towards the product. All right, if you add more SO2, SO2 is a reactant, so equilibrium will also move towards the product. But if you remove more from SO3, you remove SO3, the concentration of SO3 will decrease. So equilibrium will move towards the product, that's towards the right. Okay? Or I can also say equilibrium will move forward. Towards the right is forward. Towards the left is backward. Please take notes, okay? So you don't confuse yourself maybe in your exam or anywhere. Okay? And if you remove any of SO2 or oxygen, equilibrium will shift towards that direction. That's towards the left, or to shift backward. Okay? So take note of that. Very, very important. All right? Now, also observe the same thing in 28. The same thing is illustrated right there. You can see what is illustrated. All right, let's quickly move because of time. The video is already getting very, very long. Now, effects of pressure. That's all for concentration. Now let's look at the effects of pressure. How will pressure actually affect the equilibrium? Where will it shift it to? The effect of pressure on equilibrium. Okay, now let's look at it. Let's look at how equilibrium shifts with respect to pressure. Now take notes and bear this one in mind. Bear this in mind. This you can see right here. Increasing pressure shifts towards the side with fewer gas molecules, and decreasing pressure will shift equilibrium towards the side with more gas molecule. Okay, what does that mean? Now observe example 29 as I explain what it means. Okay, example 29 actually get to this point. Now observe as I explain what it means. You can see right here that is also the Haber process. Haber process is that reaction where nitrogen and hydrogen combine to form ammonia. Just store that at the back of your mind, okay, because you come across it again in non-metals and their compound. All right, now ammonia production when nitrogen reacts with hydrogen is called Haber process. Now observe very well, look at it very well. Let me zoom in. Observe this reaction very well. You will see that 1 mole of nitrogen is reacting with 3 mole of hydrogen to form 2 mole of ammonia. Okay, when you're talking about mole, you know the number of mole by looking at their coefficient. I already told you where coefficient stays. It stays at the front. So you can see that this is 3 mole of hydrogen. You can see that this is 2. 2 mole of ammonia, and you can see that of nitrogen does not have any number right there, trying to say that there is actually 1 there. So the 1 for nitrogen and the 1 and the 3, sorry, for hydrogen combine, making it 4. Okay, while for the product side you only have 2 mole of ammonia right here. So that's why I said in total that on the left side you have just 4 mole. That's 1 mole of this guy, 3 mole of this guy. And then on the right side, you only have 2 mole of this. So on the right side, you have 2 moles. So remember that they are all gases. So pressure is only effective for gases. All right. Now that you know that the reactant side has more gas moles than the product side, it means that if you increase pressure, equilibrium will shift to the side with lower moles. Okay, it will shift to the side with lower moles. While if you reduce the pressure of the system, equilibrium will shift to the side with higher moles of gas. Okay, very, very important. You should take note of that. So in this particular equation, in this particular equation, you can see I clearly state it that increasing the pressure, follow here, that increasing the pressure shifts equilibrium to the right. Why? Because at the right you have lower gas mole, and on the left you have higher gas moles. Okay, now observe example 30. Okay, observe example 30. Get to this point. All right. Now observe example 30. You can see that in example 30, you can see that there is 1 mole of hydrogen, 1 mole of iodine combining to form 2 mole of hydrogen iodide. So on the left side you have 2 moles in total, 1 for hydrogen, 1 for iodine, and then on the right you have 2 mole of hydrogen iodide. So both sides you have equal moles. So at this point in time, what do you think? Increasing pressure, will it shift it to the left or shift it to the right? No, it will not shift it anywhere because the moles are equal. They are the same. So equilibrium does not know where to shift to. So it means that whenever you have equal mole on both sides, it will actually, pressure change will have no effect on the system. Okay. Now example 31. Observe the reaction up there. Observe the reaction and observe this reaction right here. Okay. And if you observe the reaction, you can see that on this side you have 3 moles of gases, 2 for SO2, 1 for oxygen. So that's just have 3 on the left, and you have 2 moles on the right. So on the left there are 3 moles, and on the right there are 2 moles. So increasing the pressure will shift the equilibrium to the side with lower moles, and then decreasing the pressure will shift it to the side with higher moles. That's it will shift it towards the left. And meanwhile, increasing pressure will shift it to the right. Okay. Now also observe example 32. All right, observe example 32. Observe example 32. You can see the equation right here. Okay, now check on the left side. Do you have any gas? No. You only have gas on the right, just 1 mole of CO2. On the left side, you have CaCO3 and it's a solid. So it means that on the left side, you have 0 mole of gas. Remember that gas is the major target here. Okay, you have 0 mole of gas on the left. You have only 1 mole of gas on the right. So you can see that the right has higher mole than the left. So it means that increasing pressure will favor the left and decreasing pressure will favor the right. Or in other words, increasing pressure will shift equilibrium to the left and decreasing pressure will shift equilibrium to the right. Okay, very, very simple. Just look at the side with higher mole. The side with higher mole will be favored by a lower pressure, and the side with lower mole will be favored by higher pressure. Okay, just according to Boyle's law, pressure is inverse proportional to volume. So if volume is high, pressure should be low, and if volume is low, pressure should be high. Okay, that's for pressure. Now, also looking at the effect of temperature. This one is very, very crucial, and you should know about it. Okay, now effect of temperature changes. Now, for exothermic reaction, what is exothermic reaction? Exothermic reaction is a reaction that gives off heat. Okay, so if the equilibrium reaction is exothermic or endothermic, there is a way you will actually go through it to know where the equilibrium will shift to, if temperature is increased or if temperature is decreased. All right, now let's go over to the next slide. Okay, now take note that for exothermic reaction, if the forward reaction is exothermic, remember that when I say forward reaction, this is what I mean. Observe this particular reaction right here. Observe this particular reaction. If A plus B gives you C plus D, that's forward. Okay, the reactant giving us product. Meanwhile, if the product is now, combining again to form the reactant, that's called the reverse or the backward reaction. Okay, so now take notes. If the forward reaction is exothermic, it means that if you increase temperature, the equilibrium constant or the equilibrium will shift towards the left, and decreasing temperature will shift equilibrium to the right. And on the contrary, if the forward reaction is endothermic, then increasing temperature will shift the equilibrium to the right, and decreasing temperature will shift it to the left. Okay, now let's look at some example for better understanding. Now take a look at this example here. Example 33. Take a look at example 33. you can see this particular reaction, and you can see it is exothermic. How do you know it is exothermic? It is because your eyes can see what is written here. Okay, you can see change in H. That triangle there means changing. It means change, okay? So change in H is equals to minus 92 kilojoule per mole. The fact that it is a minus means that it is exothermic. But if it is a plus, it will mean endothermic. Please take note, okay? That's what you should look for whenever you are working with either exothermic reaction or endothermic reaction. You have no business with 92. No. Just observe if that sign there is a minus sign or a plus sign. If it is a minus sign, then you are actually working with exothermic reaction. If it's a plus sign, you are working with endothermic reaction. Okay, so this is exothermic reaction. Now that it is exothermic reaction, what should come to your mind? It means that if you increase the temperature, equilibrium will shift to the left, and if you decrease the temperature, equilibrium will shift to the right. Okay, or in other words, if you increase temperature, equilibrium will shift backward. It will shift equilibrium backward, or it will favor the backward reaction. And then if you decrease the temperature, equilibrium will shift forward. That means it will favor the forward reaction, or you can say it will favor the production of more products. All right, no, backward reaction is favoring reactants, so forward reaction is favoring products. Okay, now let me use another analogy to explain this so that it will stick very well to your head. Now imagine that you are in your room. Let's say the room is very, very, very hot. Your room is very hot. You are just there. You are sweating. Remember that exothermic reaction is giving off heat. Okay, exothermic reaction is giving off heat. So take for instance, when you set your wood on fire, or you set dry leaves on fire, you see that heat is coming out. Okay, that heat is coming out means that it is exothermic reaction. All right, exothermic reaction give off heat. Endothermic absorb heat. So if you see a vessel where endothermic reaction is occurring, that vessel is usually very, very cold. Okay, very cold, because all the heat in the area has been absorbed, so everywhere is becoming very, very cold. Now assume you are in your room. The room is very hot. It's hot for you. You are sweating very well, and me, I am in that your room, and to me the room is kind of cold. The room is cold to me, and it is hot to you. So at that point in time, your mom step into the room and see you, and that you are very hot, you are sweating, and your mother look at me, I am very cold, I am shivering, and your mother went to where the air conditioner is and turn it off, and went to where the heater is and turn on the heater and increase the temperature of the room, lock all the doors, lock all the window, off the fan, and then the place become very, very hot. So will you be comfortable? No, you won't, because you have already been feeling hot before, and now they are turning on the heater. They are locking all the windows, locking the door, offing the fan. You will become very, 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 very hot, and you will never be comfortable. Why to me that was feeling cold? Now that they have turned on the heater, they have locked the curtain, locked the door and everything, I will feel better. I will now like the room. Why? Because I was cold before, and now they are supplying heat to me. They are supplying heat. Meanwhile, you are already hot. They are supplying you more heat. So at that point in time, supplying heat to that room will favor me, and it will not favor you. So that is what exothermic reaction and endothermic reaction looks like. Okay, now assume that you are exothermic because you are the one feeling hot, and I am endothermic because I'm the one feeling cold. So at that point, when your mother begins to supply heat from the heater, for me that is endothermic, the heat favored me. And for you that is exothermic, the heat did not favor you. Okay, so in the same way, in a chemical reaction, if you see that the reaction is exothermic, like this one you can see on your screen now, you can see minus 32. The reaction is exothermic. I mean, the forward reaction is exothermic. So it means that if you want the forward reaction to be favored, Biko, don't increase temperature. Remember when you were in that room just now, we increased temperature and you almost died. So don't increase temperature. Instead, reduce the temperature. Okay? So if it is exothermic reaction, reducing the temperature will favor the forward reaction because the forward reaction is exothermic. Okay? On the contrary, if you now go ahead to, increase the temperature when the reaction is already exothermic, it will not favor the forward reaction. Instead, it will favor the backward reaction. Okay? So for exothermic reaction, exothermic is already giving off heat. So if you now go there to supply heat again, giving more heat to the guy that is bringing out heat, like you will really hinder the forward reaction. The forward reaction will not be favored. It will be hindered. So it will favor the backward reaction. But if you see that it is bringing out heat exothermic and you say, oh, it's bringing out heat, please reduce the temperature. Once you now reduce the temperature, it will now continue to favor the forward reaction. Okay, I believe with this, everything should be clear. All right, now that is for the exothermic reaction. So in this case, I can now boldly say that increasing the temperature, I can now say that increasing the temperature will shift equilibrium to the left, okay, because it is exothermic. But if I reduce the temperature to shift it to the right, okay, and I believe it is making enough sense at this point. Okay, now also watch example 34. All right, now you can see the reaction. It's exothermic. Okay, don't worry, jam will not always write heat here. They will just give you this value. They will give you a value and tell you that it's negative. So that's what you will use to know that it is exothermic, whether jam, wire, neko, or whatsoever. Okay, but this is an exothermic reaction. All right, the fact that the heat is on the product side is telling you that this thing is producing heat. If the heat was on the reactant side, then it means that heat is being absorbed. That's endothermic. All right, now in this case, since it is exothermic, it is giving off heat. Decreasing the temperature will shift the equilibrium to the right, or it will shift it forward. Okay, it will shift it to the right. Meanwhile, intensifying or increasing the temperature will shift it towards the right. Okay, now I believe that is clear enough. Now let's also observe example 35. Okay, let's observe example 35. All right, this example 35 continues to this point. Now observe example 35. You can see that this is the reaction. Observe the change in heat is a positive value, plus 58. So that plus then means that it is endothermic. Okay, just imagine me in that your room the other time. Okay, when I was feeling cold, you are feeling hot. Okay, because I was feeling cold, your mother increased the temperature and I was okay. So in the same way, this particular endothermic reaction is feeling cold. Remember I told you before that in the laboratory when you are carrying out endothermic reaction, the containers you are using are always very, very cold. Okay, now in this endothermic reaction, if I increase the temperature, wow, I increase the temperature for a guy that is feeling cold, it will just favor the forward reaction. The forward reaction will proceed very fast. Everything will just be moving forward. Everything will be moving fine. But if I now go ahead and decrease temperature for a guy that's already cold, then it will now cause the opposite. It will now favor the backward reaction, okay? Or it will shift equilibrium to the left, right? Now, that is for that. Also observe example 37. Okay, also observe example 37. The same thing is illustrated here, example 37, okay? Now, example 37, you can see N2O4 and NO2 mixture is sealed in a sealed tube, sorry, at room temperature are brown. Let me just zoom this thing out, okay? Now, N2O4 and NO2 mixture in a sealed tube at room temperature. So now the tube is placed in ice water. Once this tube is placed in ice water, what will happen? It will shift equilibrium to the left. Why? Because if you observe the reaction, the reacting system here, this is the reacting system for N2O4 and NO2. Okay, you can see heat on the reactant side, meaning it is endothermic. Okay, that's the same thing that was illustrated right here before. All right, you can see right here it's endothermic. So if you are now putting them in a sealed tube and you are putting in a tube of ice water, of course you are trying to reduce the temperature. Once you do that, or more, it will not be favorable for endothermic reaction. So it will shift equilibrium down to the left, or it will favor the backward reaction. Anyone is correct. Okay. Now the same thing is seen in example 38. Now let's go to the effects of catalyst. We have seen concentration, we have seen pressure, we have seen temperature. What about catalyst? What can a catalyst do? What can a catalyst do? Effect of catalyst. This one is very important. Like, what can a catalyst actually do here? Okay, please take note that a catalyst speed up both forward and reverse reaction equally. Okay, remember that increasing temperature, decreasing temperature that we have been talking about, they either increase the forward reaction or increase the backward reaction. But you see catalyst, it will increase both the forward and backward equally. So in doing so, the outcome is that the equilibrium will be reached faster. I mean, the reaction will reach equilibrium very quick. But there will be no change in the equilibrium position. The equilibrium position will not go left, it will not go right, because both reactions are proceeding equally. So constant will not go anywhere. And the value for the equilibrium constant, which is K, will not change. But meanwhile, the system will attain equilibrium very, very fast. Okay, so you can see this particular example right here. You can see nitrogen reacting with hydrogen. This is the same Haber process we have been using before. And you can see that when you add ion catalyst, what will happen? It will speed up both. It will speed up equilibrium. It will speed up the reaction in both directions, that's forward and reverse. But the equilibrium will be reached faster and it will not change. Okay. Equilibrium is reached faster, but the final amount of ammonia remains unchanged. Okay. Now let's look at this example 40. This is the kind of question that JAM will give to you. Okay. Not only JAM, but POSITME too, especially if you are going to schools like Uniben and some other schools like UI and the rest. Now, look at the question. It says, which of the options shift equilibrium towards the right for this particular equation right here? So which of these options will shift that equation, the equilibrium, towards the right? Now, option A says adding a catalyst. I just told you now that catalyst does not shift equilibrium anywhere. It only help you to attain equilibrium very fast, but it will not shift it anywhere. All right, that's for catalyst. And option B says adding SO2. Now observe that SO2 is a reactant on the left. And remember that whenever you add a reactant, whenever you add to any side, whether reactant or product, equilibrium will shift away from that particular side and shift to the opposite side. So if you now add more SO2, SO2 is already on the left. So if you add more SO2, I expect equilibrium to shift towards the right. Okay, that's towards the side of SO3. Okay, so option B will actually cause equilibrium to shift to the right. Option C says decreasing pressure. Decreasing pressure. Let's see if decreasing pressure will shift the equilibrium to the left or to the right. Now observe carefully. This is 2 mole, this is 1 mole, and this is 2 mole. So total of mole on the reactant side is 3, total of mole on the product side is 2. So if you decrease the pressure, it will favor the side with higher mole, which is the left. So decreasing pressure will shift equilibrium to the left, not to the right. And option D says increasing temperature. Well, they wrote in a bracket right there. You can see the brackets. I mean, this particular brackets. You can see they wrote exothermic reaction right there. Okay, so they are trying to tell you that this particular reaction is exothermic. All right, so increasing temperature, what will it do? Hey, how can the reaction be exothermic, giving off heat, and you want to increase the temperature? If you increase the temperature, you have hindered the forward reaction. You're only going to favor the backward reaction, meaning equilibrium is going to shift towards the left, not to the right. So the only correct answer there is option B. All right, now take notes. Take notes. Catalysts do not shift equilibrium. I'm saying this again now. All right, now the summary of everything is seen in section 5. Okay, now take note that concentration can shift the position of equilibrium, but it cannot change the value for K. Okay, it cannot change the value for K. Same thing with pressure. Pressure can shift equilibrium, but cannot change the value for K, which is equilibrium constant. Temperature is the only factor that can shift equilibrium and also change the value for equilibrium constant. Meanwhile, catalyst cannot shift equilibrium and cannot change the value for K. So take note, catalyst cannot shift equilibrium, cannot change value for K. Temperature can shift equilibrium and also change the value for K. And pressure and concentration, they can only shift equilibrium, but they cannot change the value for K. All right, now let's look at this particular question. Okay, it's a jam style problem. Not that it's a jam pass question. No, it's just a question that looks like it. All right, now which describes equilibrium? Which of the options describes equilibrium? Which of these options accurately describe what equilibrium is? Option A says forward reaction stopped. No, that's wrong, because in a reaction at equilibrium, forward reaction does not stop, it continues. The same with backward reaction. Backward reaction and forward reaction, they always continue. If any of them stop, the reaction is no longer at equilibrium. Option B says concentration equal. I told you, concentration remains constant. That's what happens when a reaction is at equilibrium, not that the concentration must be equal. No, they must be constant. And option C says forward rate equals to reverse rate. That's very correct. The forward reaction must proceed in the same speed with the backward reaction for we to say that the equilibrium is, the reaction is at equilibrium. And option D says that the reaction ceases. No, if reaction ceases, what is not the point of even calling a reaction? So for a system to be at equilibrium, the reaction must continue. Now, number 46, you can see this particular question. Okay, this particular question right here. All right, now the question says, you can see the equation first of all. You can see this is the equation, and then the question asking which of these options will increase the production of hydrogen. Take a look at the equation. You can see that hydrogen is actually a product. Okay, hydrogen is a product. So what the question is trying to say is that which of the options will shift equilibrium to the right? Okay, because if equilibrium is not shifted to the right, then more hydrogen will not be produced. Hydrogen production will not increase. So we are looking for the option that will shift equilibrium to the right. Okay, so option A says adding hydrogen iodide. Look at the reaction. You can see that hydrogen iodide is a reactant. So if I add more hydrogen iodide, equilibrium will shift away from it and shift towards the product. So adding hydrogen iodide will increase hydrogen production. Option B says removing iodine. If I remove iodine from this equation, look at it. This iodine is a product. Remember that if you remove from the product or from the reactant, equilibrium will shift towards that direction. So removing more iodine will also lead to more production of both hydrogen and iodine. Okay, so option B is correct also. Option C says adding a catalyst. Remember that catalyst does not shift equilibrium anywhere. So option C is wrong. So the answer is option D, which says both A and B. Now observe example 47. Look at this reaction. Look at this reaction here. Now the questioner is what will be the effect of pressure on this particular reaction? You can see right here. What will be the effect of pressure? So in this particular reaction, if you increase pressure, first of all, observe this is 1 mole of nitrogen, this is 1 mole of oxygen, and this is 2 mole of NO. Okay, so that means that there are a total of 2 mole on this side, a total of 2 mole here. So the mole is equal, meaning that if you increase pressure or decrease pressure, it will not shift the equilibrium anywhere, because increasing or decreasing pressure will only shift equilibrium to the side. Increasing pressure will shift equilibrium to the side that has lower mole of gas, and decreasing pressure will shift equilibrium to the side with higher mole of gas. So since both sides has equal moles, so it means that the equilibrium will not shift anywhere. All right, now observe question 48. Okay, observe question 48, example 48, sorry. Now example 48, you can see the equation right there. What if you increase the pressure? What will happen? On the right you have 2 mole of gas, on the right side, on the left you have 2 mole of gas, on the right side you have 1 mole. So if you increase pressure, I expect the equilibrium to shift towards the right, which has only 1 mole. And then for example 49, sorry, this is example 49. Okay, now for example 49, you can see the reaction and you can see that this is exothermic. All right, this is exothermic. You can see the negative sign for 92. So the question is, what will happen if I increase temperature? If you increase temperature for exothermic reaction, what do you think will happen? Of course, the equilibrium will shift to the left, because the forward reaction, which is the one to the right, does not need more heat. So the answer is that equilibrium will shift to the left, okay, leading to more production of nitrogen and hydrogen and less production of ammonia. Now, example 50. Example 50. This example 50, okay. You add a catalyst to a reacting system. What will happen? The answer is D, no effect, okay. It will not shift equilibrium to the left or right, and there will be no increase in K. So that's for that. Now, example 51. Look at the reaction, and you are asked to write the equation for the equilibrium constant. All right. So what are you going to do at this point in time? Look at the products NO and H2O. You know that those guys should be on the numerator and raised to the power of their coefficients. So observe all the options. You see that only option B satisfies that. In option A, you can see the reactants in the numerator. In option C, you can see the product on the numerator, but they are not raised to the power of their coefficients. Option D, you can see reactants on the numerator. That's wrong. So the answer must be option B. And you can, even option B, you can see the reactants in the denominator and they are raised to the power of their coefficients. Now, also the same thing happens here in example 52. Okay, in example 52, you can see this, and you are asked to look for the equilibrium constant. Okay, you can see that CaCO3 is a solid, CaO is a solid, so those guys cannot be a part of the equation, only CO2, so making option B the correct answer. Now that we have known this, it's also very important you take note of this guy. Common mistakes to avoid in your exam hall, both as a JAMB student, WAEC student, NECO student, post-UTME student, and whatever student that you have. All right. Now, one mistake we often see with students is that they want to think that catalyst can shift equilibrium, which is very wrong. Take note, catalyst does not shift equilibrium for any reason. Okay, so catalyst can't really shift equilibrium. All right. Now, oh, sorry about that. Now take notes. Catalysts do not shift equilibrium anywhere. Okay, now including solid and liquid in KC. Meanwhile, only gases and aqueous can be included. Please don't ever make this mistake in number 2. Okay, now number 3, confusing exothermic and endothermic temperature effect. Please take notes. For endothermic and exothermic reaction, if you increase temperature for exothermic, it will shift equilibrium to the left. If you decrease temperature, to shift it to the right. While for endothermic, if you increase temperature to shift it to the right, decreasing temperature will shift it to the left. And number 4, thinking pressure affects all equilibria, which is very, very wrong. Pressure only affects gases with unequal moles. If the moles are equal, pressure will have no effect. Now, number 5, believing that K changes with concentration and pressure. No, it is only temperature that can change the value for K. Okay, not pressure, not concentration, not catalyst. All right, but meanwhile, they can shift equilibrium, but they cannot change the value for K. Now, number 6, thinking equilibrium means equal concentration, which is wrong. Equilibrium only means that the reaction is happening in a constant rate, and all the concentration are constant. It does not have to be equal. Now, Also, number 7 and number 8, students often assume that reaction stops at equilibrium. Meanwhile, reaction continues. And also, forgetting coefficient exponents in Kc expression, meaning when you are writing the equation for equilibrium constants, you must not forget their coefficient. You must not forget to raise them to the power of their coefficients. So with this, we have come to the end of this particular video. If you have any question, do well to drop it right there on the comment section, and then I will attend to it. Okay. And also, if you are visiting us for the first time online, please do well to subscribe to this channel if you are watching on YouTube, and if you are watching on TikTok, do well to follow our page. Okay. Thank you for watching. See you in the next class. And also, let me not forget, there is a link in the comment section if this is TikTok, and if this is YouTube, check the description for this video. You see a link. You can click on it and it will take you to a CBT that we have prepared for this lecture. So you can use that to test your understanding, to see how much you understand as regard this particular topic. Okay, thank you for watching. See you in our next video. Bye bye.